So the next problem is that we have two edges, one, as you'll see, on top of the other upside down. And what we want to do is find the minimum acceleration of the bottom prism and also find the maximum acceleration of the bottom prism. You know, would treating these blocks as one system be of any use to us?
So we do have friction.
Yes. And the angle here is theta and the angle up there is theta. I guess the one thing to look at would be whether we should treat the blocks as one system or as two different systems.
Well, you have your choice. So first of all, I want to simplify this problem. I want to do it without friction to start off. So this is 1, this is 2, this is the force.
Wait. So how can there be no friction? Isn't friction the only thing holding up that second block?
Okay, say that I didn't push it at all, and there was no friction. What would happen?
It would slide off.
Right. This one would slide down, because this one, if there's no friction in the bottom here. Now, what if I came along and pushed it incredibly fast?
There's a component of the normal force that's pushing it up and holding it up.
Normal force, that's right.
And so basically, this thing would get launched into the air. Therefore, in between, you might think that you could find just the right force such that it would be balanced. No force that slides down, lots of force that gets shot up, goes up, intermediate force. So now the question is, find F that implies no slip. And then your question, Ryan, is the whole system. And since they're not slipping, they have the same acceleration, so I can do that. Okay? So what's going to happen is Newton's third law in the x direction, Newton's second law in the x direction, the sum of the forces in the x direction equals the total mass times the acceleration. And this is equal to F, and the masses are given. So therefore, I can find, I'll just write it out, A equals F divided by m1 plus m2. That tells you the acceleration that goes with F. But it doesn't tell you what any of the forces are. And it doesn't tell you, it just says F is related to A, but it doesn't say how big it is. Okay, so what do we have to do next?
Should we look at the internal forces?
Okay, so let's just look at one system. So we'll look at the internal force. And so let's just take a look at system equals block 2. And let's draw the force line. All right, there's gravity, and there is a normal force, which we don't know how big it is, but that's what we're going to hopefully find out, or at least some relationship between that and other things. Okay, now we also know that this thing is going here in the x direction with acceleration a. So again, this is Newton's laws applied, and that means F equals ma. So we look in the x direction, and we have, now let's see, this is studied theta.
Yeah.
And so we have in the x direction n sine theta, and then we have mg, m2g, but that's going straight down, and this is equal to m2a. Another equation, now the y direction up and down, is n cosine theta minus m2g equals m2ay. And what's the y acceleration of block 2?
This is 0, because it's just, we're trying to find where it stays on, right?
Trying to find where it
So
stays.
0.
So this is equal to 0. So right away, that expression there says n equals m2g divided by cosine theta. Now I can plug back into here, and I can say m2a equals n sine theta, and the result of that is going to be that a equals m2g over cosine theta times sine theta, and this is m2a. So the m2's cancel out, and a equals tangent theta times g. Okay, I like that answer. It's got obviously the right units, proportional to g. I think everything should be proportional to g. And now I can combine this with this to find the force. Okay, so I didn't have to use the F equals ma equations for block 1. Had I done so, I wouldn't have had to use the F equals ma equations for the whole system. But it turns out that it was a little bit more insightful to do it this way than to work through the equations for block 1 and then show that the x components of the normal force cancel out, blah, blah, blah. Okay, now this is simpler than the problem that we actually were given. So how do we make this problem into the one that was actually given? Say we're going to have some friction, and we're trying to find the max allowed F. And whenever we have friction, what do we have to figure out first?
Okay, so if we're looking for the maximum acceleration, the friction, so the block's going really fast.
So we're trying to push the block really hard.
And without friction, the block would fly off the top, so friction must be acting sort of downwards, to the right.
So, exactly. Good analysis. If the F were really big, what's the maximum force, max acceleration? Then we know that this thing is going to get thrown off, accelerate up the plane essentially, and that friction is going to try to prevent that. And so the friction force is going to act here, and it's going to be down this way. Now, what kind of friction is it? Kinetic? Static? Static.
Because we don't want it to be moving.
Now, what's the expression for static friction? So this is a problem for a lot of people.
The static friction is not just one value, but the maximum.
Less than or equal to.
Yeah.
Then what?
Mu normal force.
Okay. Now, in this case, can you argue that it is an equal sign? Otherwise, you have to determine the static friction from the constraint on the acceleration that things are static, and it may take little force. Okay, so I'm standing here. There's some static coefficient between me and the rug. Maybe it's 0.4. The rug's not usually very slippery. But that does not mean that my normal force times 0.4 is the static friction, because I'm standing here and I'm not accelerating to the right or to the left, and so the net x force on me better be 0. And that would be the only thing in the x direction that can be on me is static friction. So the static friction is 0, and then even if I started to move, to accelerate, the static friction would only be big enough to make me accelerate as fast as I accelerate. And as long as that was less than the force is less than the static friction times normal, and until I get to the point where I start to slip, that's the only point you can apply this equality. But here, this says what's the maximum force you can have. So that means that it is on the verge of slip through. So, okay, so we can say here F equals the static coefficient of friction times the normal force, and it's operating in that direction. So now there's going to be a component of force in both of these equations. There's going to be a component in the x direction, which is F cosine theta, and there's going to be a component in the y direction, which is minus F sine theta. So solving these equations is going to be less straightforward than it was before. But, okay. Now, I think there's one more query relevant to this question.
Yeah, so in the next problem, same setup, except no friction here. And there's a block on top. And here there's friction between this wedge and this block.
Okay.
And actually, the only question we have for this one is, what system do we want to take? And what things can be combined as one system?
Okay, so maybe this is 3. Let's just call it M3. Okay.
Mm-hmm.
What system do you want to take? What would you like to do?
So we'd like to make everything still accelerate with the same acceleration. Static problem. You could take these two things to do the same system.
Well, with or without 3?
Without 3. Could you take all of them to be the same system?
They have the same acceleration.
And
So,
that's what we want, and so we can.
okay, fine. Then, yeah, you just say, well, for the first part, I'm taking the system as being everything, I just add in an M3 there, right? And for this part here, I would just say I would take blocks 2 and 3, and so here, every place I had an M2, I would just make it M2 plus 3, and so on. So I would actually get exactly the same result. Now, having made that assumption, though, there's one thing. At the end, you have to check that everything's accelerating the same. What condition does that impose on the problem? You want to satisfy F equals MA for block 3. And so if I look up here at block 3, here it is. The normal force, there's an M3G, and since it's not accelerating slipping, it's not accelerating up and down. So AY equals 0. And so in this case, the normal force will equal M3G. Okay? But how do we make it accelerate in the x direction, horizontally?
Add a friction force?
Yes, it has a friction force. So I can go over here and say, all right, so I'm going to have F3, right, the friction force on block 3. So when I look at the x forces, some of the, on block 3, the x forces, I find that it's F3. And F3 has to equal M3 times A, and this is the same as the A all throughout the problem. So now I know that I have static friction, right? So F3 better be less than or equal to mu3 and times the normal force on 3, and we already solved for that. That's M3G. The implication is this all works only if mu s is greater than some amount. Basically, it's got to be bigger than the tangent of theta, I think, will work out in the end.